Okay, today's lecture is going to be on radioactive decay. But in order to understand radioactive decay, we have to go through a little bit of quantum mechanics and this thing called tunneling. So we're going to find some interesting information here and then apply that to learn what radioactive decay is really going on. So particle physics is also involved here. And the first thing we need to discuss is the forces. We have 4 forces. The ones that we learned about first semester: first, gravitational force. Then we learned second semester magnetic. Now there are 2 more forces that only apply in nuclei, and those are the weak nuclear force and the strong nuclear force. Now, when we talk about these forces, we're obviously getting a little more theoretical than we usually do, but we talk about something, a particle mediating a force. So what does it mean to mediate a force? It means that that's the particle through which the force is transferred. So for instance, I might be standing next to you and you push me. You applied a force to me. What mediated the force? Well, it was the contact between you and me, is what we would say. Now, we could extend this a little bit, and we could be each standing on a skateboard with our skateboards aligned, so it's one-dimensional, so we can move toward or away from each other. And you could have a medicine ball, a big, like 5-kilogram ball, and you throw that ball to me. Now, when you throw that ball, you're going to recoil backward because of the force that you applied to that ball. And when that ball comes to me and I catch it, I'm going to recoil in the opposite direction because of that ball. And so we started with us both stationary, and we ended up with both of us moving away from each other. And we would say, okay, you applied a force to me through the mediating particle of that medicine ball. And so that medicine ball is what mediated the force. When you threw it, you had your reaction to the force. When I caught it, I had my reaction to the force. So we actually talk about all forces as being mediated like this. So we have the gravitational force. We say there's a particle that mediates the force, and this particle is called the graviton. And I mentioned this first, even though it's the last one for us to have any information at all about. The electromagnetic force is mediated by the photon. That particle of light, the photon, is the thing that mediates that electromagnetic force. So we say that any force that occurs between charged particles, there was a photon, or oftentimes we say a virtual photon, that passed between them to mediate the force. And then we have 2 more forces, the weak nuclear force and the strong nuclear force. So we're going to learn a little more about those coming up. So in particle physics, this is how we indicate a reaction between 2 particles. So in this case here, the arrows are a little confusing. What this means is we had an antiproton or an anti-electron, and the arrow is reversed because it's an antiparticle, and an electron that came and met together, and they annihilated, and they produced a photon. So this is the photon, and then that photon produced a quark. Well, there's the quark, an antiquark pair. So this antiquark is going like this. And so we have the photon mediating the force. And right now you're probably, oh my goodness, what are we doing? What is going on here? Well, it's actually important for us to understand what's going on with radioactive decay to have some background on this. So the electromagnetic force, when you get to particle physics, yes, they draw these all the time. By the way, this is a gluon. That's the particle that mediates the force between the quarks, the strong nuclear force. But we have only a small amount of elementary particles, particles that can't be broken down to smaller things. And so the first group we have is the quarks. Quarks, it's a made up term. Um, it comes from James Joyce's Finnegan's Wake. But the quarks are what we consider the fundamental particles that protons and neutrons, things we call baryons, are made of. So baryons, which includes protons and neutrons, are made up of 3 quarks. Now the quarks, notice there's 6 of them here. Each one has its antiparticle. So some people say, well, there's 12 quarks. There's the up and the anti-up, the down and the anti-down, and so on. You have up and down are the lowest energy quarks. That is, they have the lowest mass. Notice the masses here are an MeV per c squared, and you have 2.4 and 4.8 for the up and down. And then we have the second generation, charm and strange, that are about 500 times the mass for the charm quark compared to the up. And the strange quark is bigger than that. It's about 5,000 times the mass of the down quark. And then we have the third generation, which goes even larger in masses. Notice these are now giga electron volts per c squared. That has the top and the bottom quark. And I was in graduate school when they finally found the top quark, isolated the last one. When I say isolated, quarks are never found alone. So isolated means they were able to determine that it was present somewhere, but it wasn't alone. Basically, you have to have an energy approaching infinity to get a quark alone. They always are found either in baryons, 3 quarks, or mesons, which is a quark-antiquark pair, or there are some more complex, like there's a pentaquark that, well, it didn't exist when I was a student, but is now, I think they have found evidence for pentaquarks. So those are the things that protons and neutrons are made of. And those are the things that we're going to focus on for the most part today. But then we have another group that's leptons. Leptons are the light particles. Light as in low mass, not light as in I see the light. And we have the electron is the first generation, lowest mass. And then it has its electron neutrino, which is an extremely low mass. The second generation, the muon is just like an electron. It'll do everything an electron will, except for it has a mass that is approximately, 200 times the mass of an electron. So it's like a super heavy electron. And it has its own neutrino. And if you notice this, the muon neutrino, its mass is actually bigger than the mass of an electron. And then we finally have the third generation, the tau, and its neutrino. Now, we're not going to talk at all about the neutrinos and their oddities, but those are leptons. And so what we deal with in life is just this first column. These are the things we deal with in life. Everything else exists, but is very uncommon, very rare. So those are the quarks and the leptons, fundamental building blocks of nature. And then over here, we have bosons. Now, you might remember from what we've just been talking about in class, bosons means they have a spin that is an integer. Notice the spins of everything over here were half integers. These were fermions. And these bosons, we have 2 groups here. The gauge bosons are the things that mediate forces. So we have gluons that mediate the strong nuclear force, photons that mediate the electromagnetic force, Z and W that mediate the weak nuclear force. And then there's one more. There's the graviton, also a gauge boson that would mediate the gravitational force. Then you have the scalar boson, the Higgs boson. We are clearly not going into any detail on that whatsoever. But these particles here, the gauge bosons, are also important to us because they're the particles that mediate forces. All right, so I've talked about these. What's the point of them? Well, let's get to strong nuclear force. You probably caught from my lecture that the strong nuclear force is the force that holds the nucleus together. And it says here via mesons, let's not worry about that. But it holds the nucleus of an atom together. It's the strongest of the four forces, but its range is very short range. It's approximately equal to the size of a nucleon, not nucleus. So if I have, let's say I have a neutron, and a neutron. Neutrons are baryons between baryons or quarks. So if I have these neutrons like this, there's going to be a force pulling this neutron to this neutron. And there will likewise be a force pulling this neutron to this neutron. But there is no force, no appreciable force between 1 and 3. There's a strong force attracting 1 to 2, a strong force attracting 2 to 3, but virtually no force between 1 and 3 because they're too far away for the force to be effective. And I put those all neutrons. I could have had, if I have a proton and a neutron, it's still the same thing. You're still going to have an attractive force pulling them together. If it's a proton and a proton, still going to have an attractive force pulling them together due to the strong nuclear force. So the strong nuclear force is going to be pulling them together. The electromagnetic force is going to be a much weaker force pushing them apart. But of course, if I had 3 of these, let me do it like this: proton, neutron, proton. Then I'm going to have the same attractive forces as I showed up above, but I'm also going to have the electromagnetic repulsive force pushing those protons away. And so we kind of have a competition. The nuclear force, the strong nuclear force, is holding things together, but it's only a nearest neighbor thing holding them together. Whereas the electromagnetic force is pushing them apart. It's a weaker force, but it's longer range. So all protons in the nucleus are repelling all of the other protons. Whereas attraction, the protons are only being attracted to protons and neutrons that they're nearest neighbors with. So that's why when you get a large nucleus, you have to have a lot more neutrons to space the protons farther away to drop the magnitude of the force between the protons while increasing the forces that are holding it all together. Now, that's the background. How does this deal with radioactive decays? Well, this here is showing us a neutron undergoing a beta decay, making a proton, and then we have the anti-electron neutrino. That's what is indicated in this picture. So now this is showing time on the vertical axis, and it shows a neutron, which is made up of an up, 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 down, down. Neutrons, if we look at the quarks, a neutron is 1 up, 2 downs. If you add up the charge of an up is 2/3. So the neutron has a charge of 2/3 plus down is a minus 1/3. So 2/3 minus 1/3 is 0. So neutrons have a charge of 0. And their spin, you have 1/2, 1/2, and 1/2. Plus or minus because they could be aligned the same or opposite. So if you put this together, you actually get values that could be 3/2, 1/2, minus 1/2, or minus 3/2, but it turns out that only those center two are what we get with a ground state neutron. Well, let's just say that's all we get. So that's how we get the spins. And then if we were to do a proton, oh, I wrote up, down, up, that is a proton. Up, down, down is a neutron. So if I do a proton is equal to, I'll put up, down, up. I usually put up, up, down just to get my order right. So the charge is equal to 2/3 plus minus 1/3 plus 2/3 is equal to 1. And its spin will have the same calculation. So that's how we make the protons and neutrons. 2 ups and a down is a proton, 1 up and 2 downs is a neutron. So in this diagram, we show the up, the down, and the down for the neutron. And the proton is an up, down, up. And so there had to be something that occurred here, and that's this here. This down decayed into a proton and a W minus. The W minus, remember, is the particle that is one of the 3 variations that will mediate the weak nuclear force. The radioactive decays are all mediated by this weak nuclear force. So they're going to involve either a Z, a W plus, or a W minus mediating the decay. But then that W minus further decayed, producing an electron and an electron antineutrino. Now, let's talk just briefly about conservation. Things we've learned that are conserved. If we were in normal class, I would ask you to list these, but you are not going to be able to respond very well, not being in normal class. So things that we've learned that are conserved. In chemistry, you learned something incorrect. You learned mass. Well, that's not conserved. What is conserved then? We have energy. Energy cannot be created or destroyed. We have charge. Charge cannot be created or destroyed. We talked about momentum, but momentum was only conserved if the net external forces equals 0. So that's only conditionally conserved. Now we're going to add some new things. So charge is already conserved. Charge is an important consideration when we're talking about particle physics. We also have baryon number. The baryon number is conserved. And we have lepton numbers. And right now, you're probably saying, well, wait, what, huh? Well, if we look at the down, I put a P for proton, that should have been an up. The down created an up in the W. The down has a baryon number of actually 1/3, and the up has a baryon number of 1/3. And so we had 1/3, 1/3, the W has a 0. And so that baryon number was conserved. Now this is actually a quark number. Each quark is 1/3. A baryon is 3 quarks. So baryon has baryon number of 1. We have the lepton number. Lepton number for an electron is 1. And for the electron, if it didn't have the anti, it would be 1. But if the anti makes it a -1. And so for the lepton number, we had 0 in the W minus, and then the electron was created, and then its anti-electron neutrino was created, so the lepton number was conserved. And so all of these things they demand that we have to conserve these things. Now there is another partially conserved, and that is quark flavor. Quark flavor is conserved if not weak force mediated. Now, the flavors of the quark, that's your up, down, strange, charm, top, bottom. You can call truth and beauty instead of top, bottom, by the way. So in this case, because we had a weak particle, that is a weak force, the W plus, minus, and Z, then we actually changed the flavor of the quark from a down to an up. So the quark flavor was not conserved in this beta decay. So this is what's going on fundamentally with the beta decay. You might remember in the regular class I said the beta decay, you're creating an electron and there was no electron there to begin with. Now you can see where the electron came from. The down decayed into an up and a W minus, and then that W minus decayed into the electron and the anti-electron neutrino. And so an electron was created. We didn't violate any of our conservation rules along the way. So that's a beta minus. What about a beta plus? Well, a beta plus, I'll have my up, down, up. And the up and down will stay the same, but then I'm going to have the up changes to a down. Now the up had a positive 2/3 charge and the down has a minus 1/3. So that means that I'm going to have to carry away something with a positive 1 charge. So it's going to be a W plus. Notice this was W minus because it was carrying away a minus 1 charge. And then that W plus is going to decay into, actually, yes, an anti-electron and an electron neutrino. Notice the E plus is the positron equals anti-E minus, or an anti-electron. So you can call a positron anti-electron, it's the same thing. The nomenclature, we don't put the bar over it, we put the E plus, but you have to understand that's antimatter. And so in this case, this has an electron lepton number of -1, this has an electron lepton number of +1, and your lepton number is indeed conserved because you had 0 with your W plus. The charge was conserved. We have conservation of everything. So this here is a beta plus decay, which we would usually write as a proton creates a neutron plus the beta plus the electron neutrino. And remember, the beta plus is just equal to the positron. The 1 here is because of the effective change in the number of protons. It's not a proton, but it is going to reduce the proton number by 1, and so that's why you put the 1 there. Now that we understand what's going on with the beta decay, let's turn to alpha decay. One model of radioactive decay through alpha decay is to look at a nucleus and say, okay, this nucleus has an alpha particle that's 2 protons and 2 neutrons, so a helium nucleus that's bouncing around in the nucleus. And each time it gets to the edge of the nucleus, this is potential energy. So the nucleus essentially has a radius that's that big. Well, actually, let me go out further. That big. That's the radius of the nucleus. And each time that this alpha particle gets to the edge of the nucleus, it has a chance of escaping. Now, the energy of the alpha particle is like this. And your barrier is up here. And so that's like saying, okay, I have a ball bouncing around in a bathtub. So it can roll up the sides. But the kinetic energy is such that if it rolls up the side, it only can go up to this elevation. But the side is up here. Is that ball going to get out of the bathtub? Well, no, it doesn't have enough energy to get up to the top of the bathtub. No matter what you do, unless you change the energy of that electron or you lower the wall of the bathtub, it's not, or electron, of that ball, or lower the height of the bathtub walls, it's not getting out. It just doesn't have enough energy to get out. But quantum physics introduces some strange things. And one of the strange things about quantum physics is we talk about the wave nature of a particle. And so we have the alpha particle is like a wave, and it has, its probability of being here is proportional to the amplitude, and its probability of being here is proportional to the amplitude. And so even though it's inside, there's a certain probability that it can be outside because of the wave nature. And so it can do what we call tunneling, where it essentially drills through and suddenly appears outside. It magically transports through the barrier. It has enough energy out here to be there, but it does not have enough energy to be in this region. But it somehow gets past that energy barrier to another allowed position because the wave nature of the particle says that there's a certain, its position has probabilities of where it is, and there's a certain probability that it's outside. And so we call that tunneling, and it's something that we observe. We really see it happening. That's the whole basis for a STM, a scanning tunneling microscope. The scanning tunneling microscope, you have a tip, and you bring it close to a surface, and you put a charge, like let's say it's a positive charge on this tip and a negative charge on the surface. And electrons from the surface are going to magically jump across, even though they don't have enough energy to jump across. And so you measure that tunneling current, as we call it, and that tunneling current tells you about how close you are to the surface. In fact, on the next slide, I have an equation to show, actually, is the next slide? Yes, I have an equation to show what the tunneling probability is, and from that you can calculate what the tunneling current is. So there's a certain probability each time that alpha particle comes to the edge of its nucleus, its well, it's an energy well, there's a certain chance that it will tunnel through. And so it's a probability problem. It's just a probability. You have a certain number of times per second that it reaches the edge of the well, and a certain probability every time it gets to the edge of the well. And that gives you the probability of decay per second. So here is something that's showing the wave function of a particle inside the well. So here's the particle inside the well. But its wave function extends through, and we just go like this, being in the well, and it asymptotically approaches zero. But because the wave function is not zero on the outside, there's a certain probability that it suddenly moves from inside to outside. And once it's outside, then it shows you the wave that it would have outside once it's outside. And so we can calculate the probability of tunneling by taking this here, T is the tunneling probability as a function of E, the energy of the particle, is equal to exponential minus 2 integral from one side to the other side of the boundary. So here's x1, here's x2. The square root of 2 times mass times the potential energy of the barrier. So here's the potential energy of the barrier right there, minus the energy that the particle has, dx. So you can calculate that, and as you would recognize, the tunneling probability is 1 if this integral gives you 0. That is, e to the 0 is 1. So what would make that 0? Well, if your energy is equal to your potential energy, then you have the integral of 0, and it would be 0. So if the energy is above this boundary, of course it's going to get out. That's pretty obvious. If the energy is lower, then you do this calculation. And this picture here is just showing what the potential energy well looks like for a nucleus. So you have the V, the potential energy that you have for the, for getting out is about 30 mega electron volts. So that's the V that you put in here. Now notice V is a function of position. So truly you have to put this thing here and there. So it's not a simple constant V in this integral. And then E, of course, is going to be the energy of that alpha particle. So how does this play into radioactive decay? I put those blank slides are supposed to come after this, not before. I was not thinking. Well, we have the decay constant, as we call it, is the probability of decay per time. And collision here means collision with the wall. So we have a certain probability of decay for each collision with the wall, which comes from this calculation right here, probability of tunneling. And then we have the number of collisions per time, which we can actually calculate just based on the total energy and the mass and the radius, just using kinematics. Kinetic energy is 1/2 mv squared. And if you take the distance that it has to travel to go to the speed from that equation as a function of kinetic energy, and the distance it has to travel to go from one side of the nucleus to the another side of the nucleus, you can calculate the time per collision, invert that, and it's collisions per time. You multiply those together, and you get the probability of decay per unit time. So how does that play in then? We haven't done a thing at calculus. We've done a whole lot of high-level physics. But how that plays into decay then is you are going to have, each time your alpha particle hits the edge, you have a certain probability of decay. And so if, I swear I did not start PowerPoint. If you have n is equal to the number of nuclei, so let's suppose that is, for instance, uranium 92, 238, the dominant species of uranium. So n is the number of uranium 238 92s, and you have lambda is equal to the probability of a single nucleus undergoing radioactive decay per second. Then you'd have the number of decays occurring per second is equal to that probability of decay per second multiplied by the number of nuclei present. Now, as I said in my lecture, there is a sign issue here that should have a minus, because your n decreases, dn is negative. So that's where that minus sign comes. It's kind of a record-keeping thing. And so this is our calculus relationship that we derive just from the meaning of what we've talked about, the probability of decay per second for each for each nucleus. So we can take this and we can solve this. We want to find the number of radioactive nuclei remaining as a function of time. So how many variables do we have in this equation? Well, lambda is a constant, the decay constant. So my variables are n and t. And so we learned first day of first semester that in something like this, we need to separate variables and then 2, integrate each side independently. So let's do that. Number 1, separate variables. Well, that means I want n's on the left side here because I want my d's in the numerator position and t's on the right side. So I'm going to have to divide both sides by n to move my n away from the right-hand side and get it to the left. And I'm going to have to multiply both sides by dt to get my time on the right-hand side. So if we just cancel, These dt's canceled and these n's canceled. So there I've separated variables. So now it's time to integrate each side. So the integral of dn over n, starting at my initial n, ending at my final n, is equal to the integral of minus lambda dt, starting at my initial time, which we set arbitrarily to 0, because why would we start time in some other time, to my final time. And if I integrate those, integral of dn over n is natural log. And then I have to do my limits. Integral of minus lambda t, t is minus lambda t, do my limits. And so applying those limits, I get the equation natural log of n final minus natural log of n initial equals minus lambda t final minus 0. Well, this here is mathematically pretty much nonsense, because you can't do the natural log of something. Well, actually the n's don't have units now that I think about it, but they fundamentally do. It's number of nuclei, so 1 nucleus, 2 nuclei. So we generally combine that to natural log of n final over n0, which of course is mathematically perfectly sensible. Now at this point, n final is the number of radioactive nuclei remaining at time t final. So I can drop off the finals, relax it, as I say. And so my equation is natural log of n over n0 equals minus lambda t. This equation in and of itself is really useful. It's really useful because we have this thing we call half-life. Equals time when n equals 1/2 n0. So since this equation is already fundamentally solved for time, I have time equals minus natural log of n over n0 divided by lambda. That is, I just divide both sides by minus lambda. Or using the fact that natural log of n over n0 equals minus natural log of n0 over n. This is equal to the natural log of the starting n divided by the ending n over lambda. So taking our definition of half-life, my half-life is equal to natural log of n0 over 1/2 n0, because our definition of half-life was when n is 1/2 n0. Well, you can see readily those n0s cancel. This is just equal to the natural log of 2 divided by lambda. And we usually indicate this with a tau rather than t. So that's an equation that tells us what the half-life is, the time for us to have 1/2 of what we started with remaining. Doesn't matter when you start. If you wait this amount of time, you're going to have half remaining. Then we also can take our starting equation and solve it for n. If I solve that for n, I'm going to have to do exponential of both sides. But the reason I did that is because exponential is the inverse function of natural log. So that just gives me n over n0 is equal to e to the minus lambda t. Therefore, the number of nuclei remaining is equal to the number we started with, e to the minus lambda t. And that's our other important equation for radioactive decay. There's one last important thing to get out of this. So we have, this is the number of remaining elements, remaining nuclear elements, and the number we started with. When you're doing stuff with radioactive material, you don't care really how much sample you have. You care about what the activity is, how many decays per second is occurring. Because if you have lots of decays per second, that means you have the potential for a lot of damage. If you have, one decay every year, nobody's going to worry about any danger of working with it. So we talk about the activity equals the rate of decay, or by definition, activity is equal to dN dt. Well, let's go up to the start. We started with dN dt equaled minus lambda n. And so I could take this relationship right here and say, well, activity is equal to minus lambda n0 e to the minus lambda t. And now I have a minus sign. Why that minus sign? Well, activity is actually minus dN dt, because dN dt is going down when you decay. And so that's going to make this a plus lambda n0 e to the minus lambda t. Okay, fair enough. Lambda n0 is the activity we started with. So activity is equal to the activity you started with, e to the minus lambda t. Notice this activity equation looks identical to the decay equation because it just depends on how many elements are present and what that decay constant is. And in fact, you could have also just said A is equal to minus dN dt equals minus d dt of n0 e to the minus lambda t minus n0 times minus lambda e to the minus lambda t equals n0 lambda e to the minus lambda t equals the activity initial e to the minus lambda t. A second way of skinning the cat. So our calculus involved with radioactive decay, the calculus itself was, at this point, it should be simple, right? It was hard first day of first semester, but we've been doing this over and over throughout the semester, separating variables and integrating. So by now, it should be pretty second nature, but we see how really simple it is that we get this exponential decay. And in fact, we see exponential decays in nature all the time. Why? Because in nature, we very often have situations like we started with here. I'm just going to rewrite what that equation was. We start with this relationship that the rate at which something happens is proportional to how many are present. Like, say we're talking about predation. The rate at which animal A is killed is proportional to how many animal A's there are present. If there's more animal A's, or let's say, I don't know, it's proportional to how many are present. And so you naturally have an exponential function. And so we see that all the time in nature just because many things are proportional to how many are present. All right, that ends our lecture. I hope you understand much better now.